Hey everybody! All right, we're moving into our next unit here in our 4U physics class. We're going to start talking about electromagnetism. Okay, um, that's a weird word, electromagnetism. So somehow we're going to talk about electricity part and magnetism at the same time. And really, electromagnetism is actually only one thing. We talked about the four fundamental forces. One of them is electromagnetism. Um, it's one of those first points in understanding of physics where we've unified theory. Important term in modern physics, talking about unification of ideas. One of the earliest ones of the 19th century unified the concept of electricity and magnetism. They're basically the same thing. In one sense, they're a relativistic view of each other. Really complicated statement there, and a lot to unpack in there. We won't go there, but electricity and magnetism are really the same thing, and we're gonna put them all under the blanket of electromagnetism. We did see a little bit of this in grade 11. Looked at motors, and we saw that electricity running through a wire, produces magnetic fields going around them, following our right hand. Current goes this way, magnetic field this way, or in a solenoid, the current was going on our fingers, and our thumb was our field. Right, so we've seen this before. Our motors, right? We saw motors, the motor principle, the remember our right hand rule of where the magnetic field was the wires, the the magnetic field was the fingers, the thumb was the wires, and the current, the force was coming for our So we've seen this before, but we're going to go a little bit farther into electricity and magnetism. Talk about electric fields, magnetic fields, how do they interact with each other. Maybe even get to something called light, how light shows up, electromagnetic wave. But we'll get there. Okay, so first thing we want to do is we want to go back, way back. Okay, we're going to go back in the Wayback Machine all the way to grade 9 and see if we remember some of these ideas from grade. First thing is the idea that all matter that we have around everywhere, is basically composed of either charged or uncharged subatomic particles. And those charged subatomic particles are electrons and protons. A little bit more complicated than that when we go into our standard model of modern physics, but for all intents and purposes, electrons are negative subatomic particles, and protons are the positive ones. An excess of electrons makes the object negative. A efficiency of electrons makes positive. And the electrons, remember, are in atomic orbitals around the atom. And so that means that they are weakly bound to the atom. Right? That means that we are able to kick them off, ionize the atom in some way, kick the atoms off of it, or we can, add atoms to it. We can change the charge by moving electrons around. Sometimes that's very easy to do in a conductor. Conductors have all of their electrons, it's called a conduction band, where all the electrons sort of um, exist in a sort of a cloud. When we talk about a conductor, say copper, that we have all the copper nuclei arranged in some sort of crystal, and then all the electrons aren't bound to any individual copper atom. All can exist simultaneously and all over the place. They can move around and do wherever they want to go. So they're able to move very, very easily. The protons themselves that make the actual structure of our atoms, of our material, are protons that are basically make what the atom is, can't move easily, unless we can move the atoms themselves, like say in a liquid where positive ions can move around, or gas. Plasmas are ionized gases. When you take a gas, heat it up enough, all the electrons are ripped from it. Have the positive nuclei flying around and the electrons flying around. We have an ionized gas, which is called a plasma, the fourth state of matter. But typically we're going to talk about solids, and we're going to say that the protons cannot move, bound in the crystalline or whatever, so wherever the structure is of the atom. That's defined by where the protons are. The electrons are able to move. So the electrons move around, the negative stuff moves around, positives don't. Remember, we move the electrons around and not the positives. And when we do move these around, we end up with electricity. Electricity is defined by the motion of electrons. Right? And if I just move them from one place to another and they stay there, that's static electricity. And if I move them using something like a battery or an electrical power source and push them around in a circuit, we end up with current electricity. So quick review of some of the ideas of grade 9. But we're going to go into the most important idea here is what we call the law of electric charges, which simply stated that like charges repel and opposites attract. So if they're a positive and a positive or a negative and a negative, they have same charges and fight against each other. Opposite charges attract each other. Very similar but different than gravity. Gravity is always attractive. There is no such thing as negative mass. Right? Negative mass would imply, using Newton's gravity, negative mass would imply anti-gravity. Sort of, instead of objects towards each other through gravity, they would away from each other, which would sort of stop the existence of the universe. But I don't know. We're going off theoretical. Weird. Okay. Anyways, let's go back to normal. Okay. Like charges repel, opposites attract. But the question is, how strong is that? And that gives us, leads us to what we call Coulomb's law. We saw this last year, where we can define a force between two charges. Did we do it last year? No, we didn't. We only did simple circuits. Okay, so here, this is Coulomb's law. Looks very, very similar. Look at this. Compare this to gravity, Newton's gravity, right? Fg m1 all over r squared. Look at that, almost identical form. Weird, eh? So it's again proportional to Q's. Q is the charges measured in something called coulombs. A coulomb is a large number of a large number of electrons, 10 to the 19 electrons. Okay, this is because this work done by Coulomb was done a long time ago, before the electrons were even known, or you can even say that an electron existed. Okay, so we have these charges Q1 and Q2. So it's proportional again. In gravity, we looked at the force of gravity is proportional to the masses. So here it's proportional to charges. Larger charges means larger force. And again, it's inversely proportional to the square. We have another inverse square law. And this again has to do with the spherical symmetry. Remember we had those nice pictures. Here's my area. And then when I got 2r away, we got to end up, 4 areas. And that thinned the force. Right? So in the same way that gravity was spherically symmetric and led to an inverse square law, charges, obeying Coulomb's law, obeying this expression here, are also spherically symmetric. So we end up again with an inverse square law. Okay? Now we have, instead of the universal gravity constant, we have this K, which notice is much, 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 much larger. 10 to the 20 times larger. Newton's gravity. So you can see the electrical forces are much, much, much stronger in the universe. Gravitational. So our electrostatic force, we're going to call it FQ. That's going to be measured in Newton. And we have our Coulomb's constant, 9, 10 to the 9 Newton meters squared, Coulomb squared. Our charges, again, measured in coulombs. And we have our distance, again, measured for all SI units. C, coulombs, right? 1 coulomb is, 1 coulomb would be 1 over 6. Okay. So that's a charge. This number here is the charge on one electron. That tells us how many. Let's not worry about that. Scrap it. Yeah, let's not worry about that. We'll go over that later. Anywho, so let's now. We got to be careful here, though. So, strictly speaking, this law is only valid for point charges, and also gravity is Newton's gravity law is only valid for point. But we can take any distribution of mass for gravity or a distribution of charges and treat them like a point charge at the center of the charge distribution. Okay? So we're able to turn a distribution into a point. So this law is perfectly valid as long as you're outside of the thing. Okay, just like the gravity between the Earth and the Moon, using Newton's gravity law, only really valid for the point charges, the point masses at the center of the Earth and the center of the mass. And using calculus, we can put it all together. Don't worry about it though. Okay, but strictly speaking, it's only valid for point. So let's see what happens if I take a 5 micro for this m, this 10 to the negative 6 micro, Greek m, lowercase m, Coulomb charge. Take two of them and I put them 15 centimeters apart. How much force is there going to be if A, they have the same charge, or B, have different charges? So what's A going to look like? So I have my force, FQ, going to be equal to A, the Coulomb constant, charge constant, Q1, Q2, all over the distance between them squared. This is going to be 9, 9.0. It's 10 to the, let's move this back a little bit, 10 to the 9 Newton meters squared Coulomb squared. All that multiplied by 5.0 times 10 negative 6 coulombs. I'm going to square that because there's two of them and they're both the same charge. That'll give me a divide by, what's this, 0.15 meters. Remember using meters instead of the SI unit. And we're going to end up with, in this case, that's 10 newtons. So I've left this as a scalar for now. Right? But really, what does that mean? This positive 10 newtons. What is that telling us? That I got a positive number. What do we know about charges that are the same? What does the law of electric charges tell us? Same. It tells us that they're telling each other. This is telling us if I have this one charge, let's call this charge. And I have the second charge, let's call this charge 2. The fact that it's positive is telling us from the viewpoint, from my frame of reference here of 1, my frame of reference is charge number 1. There's going to be a positive, so this is radially outwards. It's in this direction, 10 newtons. It's pushing it away. Okay, that's what that positive is telling us. We can, if we want to be a little fancy here, we could put a vector sign on this. And we could put a little r hat. That r hat, we call that a unit vector, and it is in the radial direction. This is a vector here. R hat is equal to radial vector r divided by the magnitude of the vector r, which really is a unit vector. It's 1 unit long vector, so it has no real magnitude, but it's in the direction of r. So I can only slap on this r hat, say that what direction it's going to be. So this will be radially outwards. So, and this is, if this is a spherically symmetric force coming out of this one, it's going to be pushing it away. Okay, that's what that positive, and this is, we could make it simpler. Let's put an F thing and let's say away. Or alternatively, you could just go 10 newtons in the r hat direction. Okay, and you can see if I do this again, what's my analysis is going to be very similar for part B, but okay, go back here. Everyone okay with that? This is a bit funky. You guys are currently, some of you are currently doing 4U physics, and you should know hopefully what unit vectors are, but maybe not. Okay, it's just just how we can take a vector and pull out the magnitude values to make it a scalar. This is basically just pulling out the vector, the directionality in the vector r. Right, so I'm taking the vector r, which is defined by free space circle. R is just the vector going outwards, directly symmetric. You guys can't see that, can you? Sorry, my head's in the way. If I have some, say, 3 space here, circle, right? Circle. Oh, that got ugly. I don't like that line. R is just the vector radially outwards. So r hat is just a directionality in the r direction. There's no magnitude attributed to it. It's a unit vector. All that. Okay, so r hat, 10 newtons r hat. Now, what that's going to tell us, though, is that for B, doing the same thing, we're just going to get negative 10 newtons. So what does that negative tell us in this case? Again, here's 1, here's 2. This is going to be attracting it, right? If this is my frame of reference is 1, this is going to be attracting 2 towards 1 because it's in the negative r direction. Imagine this. R direction here, some axis, R in the R axis, let's say. The negative means it's going to be coming towards it. So the law of electric charges is actually buried in Coulomb's law, right? Because it's, what was it, K, Q1, Q2, all over R squared. So this idea that we're multiplying these charges, and some of them can be positive, some can be negative, is buried within Coulomb's law. Law of electric charges is in there mathematically. These awesome things that just we have these heuristic ideas we throw at you in grade 9 and 10, and now at this point we can get to the analytical part to actually see where those concepts come from, and it falls out of the math. Okay, let's try another one, a little bit more complicated. We have an object with 3 microcoulomb charge, positive 3, and we have another one that's negative 5 microcoulomb. And there's some distance apart. They don't tell us what the distance is, but they tell us that the force between them is 2 newtons. We're going to touch them together, put them back to the same distance. What's the new force going to be? Let's think about this for a second. What's going to happen when I take a positive charge object, negatively charged object, and touch them to each other? What are they going to do? What's going to happen to the charge on the two objects? One's positive, one's negative. They're going to attract each other. Or then when they do actually touch, when they're allowed to pass electrons between them, let's say they're conductors. There's the word, conductors. They're going to distribute the charge around each other to get into a new state of equilibrium. It's going to spread out. So what's the new charge going to be? Positive 3, positive 5. Charge going to be? It's going to be the average of the two. Let's figure out what the new charge is going to be. So, and this will be the same for both. Call this Q prime. That's going to be 3. I wrote down. Positive 3 plus negative 5 divided by 2. It's going to be negative 0 coulombs. That's going to be the charge on both of the objects afterward. Okay? So we can then, now let's do a little bit of analysis here. So we're writing down Coulomb's law, F is equal to K, Q1, Q2, all over R squared. Now it tells us that the force on this is 2 newtons. We know what K is. Let's not worry about it. Let's leave it. We don't know what R is. I'm going to leave that for now. And we do know that the charge on Q was positive 3 coulomb. And the charge on Q2 was negative 5. So this is before. Okay, let's write that down. This is the before scenario. So I can work this out to say that that's going to be 15, 2. So K over R squared is going to be 2 over 15. What are the units going to be on? Newtons. Newton meter squared. Coulomb, so it's being newtons per meter squared. Okay, so 2/15 Newton meter squared for the this K over R squared. Okay, the coulombs have canceled out because I got rid of them. Okay. So, what's going to be next? So that's going to be before. What about after? So afterwards, F is going to be K Q1 over R squared. But in this case, right, my new force, I don't know what my new force is going to be, but it's going to be K over R squared multiplied by the new charge, which is negative 1 coulombs squared. Oh, that's wrong. That should be. Okay, so now that's going to be 2/15 newtons coulomb squared multiplied by negative 1 coulomb squared. Negative times positive. So we're going to end up with what? Oh, wait. It's negative, so this will be negative here. Here. So we're going to have negative 0.13 newtons. That's my new force. So they're going to repel each other. Started off attracting each other, right, because they're opposite charges. Right? So from this attraction, but because this is negative, this is now going to tell us a repulsion. Oh, no, wait. Yep. Okay. So I'm going to get negative, from here I got this K over R squared, negative 2/15 term. Okay. It's going to have a negative times a negative, that's going to be positive, end up with, oh no, what am I saying? Yeah, that's a repulsion. Okay. Now you may be wondering, okay, so we said in the last thing that negative meant, go back here quick, back here. In this case here, I said that negative was telling us that they're attracting, positive was repulsion. Now notice the difference here. Now what I've done is I've said this is positive. So that positive 2 newtons was telling us that it's the frame of reference I defined was telling us that positive was the attraction, so the negative would be the opposite. Okay, so that is a little bit confusing. I apologize. If I go back to this example, I used positive to imply going away, but because of my definition here at the beginning of my problem, I should have made that negative. That would have probably made things a little bit easier to see. Okay, so that negative, that positive there I put for the 2 newtons meant I just did a change of sign for my reference. Okay, but just know that this was positive and this was negative, so one was an attraction and one was, again, remember, there is no correct frame of reference, but sometimes there's one that's better, and probably could have used a better one. Okay, so the signs do get a little bit tricky. Okay, so let's try this one. This is a little bit more complicated because there's 3 charges now. Okay, so I have this charge C. This is going to be my frame of reference. Okay, so this is C. This is my frame of reference. Let's think about it before anything happens. Okay, so we know that this is a negative charge at C, and it's going to be feeling an effect of this positive charge B. So what is a if let's say nothing can move, but what's it going to feel? What's it going to feel from, like, this is a positive and a negative, so positive and negatives, what do? Attract. So there's going to be a force upward that we can define as force of C. In the same vein, we can say that this force A is going to be pulling the up there. So we can say there's a force here, F of A, C, upwards. Feel. It's the net force that this feels. If they were all positive, I'll be pushing in the opposite direction, but we're attracting it. So let's figure out each of these individually, F of A on C, and then add them up because they're vectors. Okay? So F of, let's do A on C first. All right, this is going to be K, U of A, charge on C, divided by the distance between A and C. Oops, why did I vector it? I meant to square that and put a vector on top of it instead. Okay, so what's that going to be? That's going to be 9, 10 to the 9, Newton meters squared, Coulomb squared, multiplied by the charge on A. A is 8, is it not? 8. 10 to the 6, negative 6 micro coulombs, multiplied by negative 2. 10 to the 6 coulombs. All of this divided by 0. Oh, it doesn't show us. Okay, so that's going to be 26. Now, where did I get 26 from? Anybody see? 10, 24. You guys ever seen the 5, 12, and 13 triangle? Well, this is one of these Pythagorean triples. And if I multiply everything times 2, 5 times 2 is 10. You don't believe me? Okay, so 5 squared, 12 squared is equal to 13 squared. Okay, that's one of these Pythagorean triples. 3, 4, 5, 5, 12, 13. This probably should remember. Okay, so using that, multiplying it by 2, we get that that's 26. We're dividing by 0.26 meters, which gives us a force of negative 2.13 newtons. Now that's just a scalar. You have to figure out what the angle is. Now you can do that by just doing a little bit of trig. It's going to be inverse tan of, this is my, let's call this my angle here, which is also going to be the same angle here. It's going to be 10 divided by 24. Opposite over adjacent, which ends up being 22.6 degrees Coulomb, Celsius, degrees. Okay, pardon me. All right, so now what's the direction going to be on that? Notice it's mostly going east. Oh, sorry, we still haven't done a frame of reference, have we? Uh-oh, bad, Mr. Stone. Let's just define quickly: north, south, east, west. So this tells me that it's going to be mostly in the west direction and a little bit north. So we can say, as a vector hat on that, it's going to be west 22.6 degrees north. Right? And then we can do the same thing, F of B on C. Okay, that one works out to just 72. I'll let you guys do that one. And in what direction? It's just in the north direction, right? Because it was only upwards. Okay, so now how the heck do I add these two vectors together? I can't. I have to break them up into components. So let's do that. So f of A on C, the x direction, right? That's going to be 2.13 newtons. And which is it going to be cosine or sine? So we want break this up. I want to break this up into two vectors. X vector, y vector. Okay. So the x vector is going to be the cosine at 22.6. Back to okay. So it's going to be 2.13 multiplied by the cosine 22.6 degrees, which is going to be 1.97 newtons. Okay, that's in my x direction. Force of A on C in the x direction, and alternatively, A on C y direction, 2.13 newtons sine 2.6 degrees, which is going to give me 0.82 newtons. Okay. And F of B on C only had a y component, which was 72 newtons. Okay, and this I'm using the, probably should do that here. I should say that this is positive, west is positive, and these two are negative. Okay, it means that all my numbers here all end up being positive. Make my life easier. Okay, and now I can add the x. I don't have any other x's. Sorry, I can add the y's together, and I can end up with. Sorry, this was. Did I say? Have I been saying 72? I meant to write 7 point. Okay, 7.2. So then my total in the y direction is going to be 7.2 plus 0.82, which is going to give me 802 newtons. And so that's my y component of my final answer. My x component is just going to be the 1.97 newtons. And then to get my total, I'm going to have to find out my f is going to be equal to the square root of fx squared plus fy squared. It's going to end up giving me 8.3 newtons. Okay. And then my angle is be just first and 1.97 divided by 8.02, which works out to 14. So therefore, after all that work, my final force is going to be equal 8.3 newtons. That's the direction it's going to be. It's mostly going. This was in the. This is in the north direction. This is in the west direction. So it's going to be mostly north, and then 14 degrees west. Okay. There's my final answer. Let me just check that number. I don't like the look of that number. 8.02 squared plus 7 squared square root. Yeah, 8.3. Okay, This is all to 2 significant. There's my final answer. Like, see, these problems do become quite challenging because we have 2 different vectors. We have to do 2 different Coulomb calculations, then break them up into components, and then work. Questions do end up quite a bit of. Okay. So we had to figure out the 2 different forces, our reference being, and then adding up the final answer. All right. So these are forces. Forces are vectors. If it asks for a force from multiple sources, you have to find all the forces, break them up into components, add the components in the same direction, get a final answer. Okay. All right. Last example here. So we have here 2 identical spheres. Okay, both of them, 20 nanocoulombs. Much. Okay. They all have a mass of 1 gram. One is fixed. The other is attached to a string. So this one here is fixed. This is stuck. This one is allowed to swing. And it's deflected by some angle here. When the charges are telling us that these charges right now are 3 centimeters apart, what is the angle of deflection? Okay, so there's 2 forces acting here, right? There's a repulsion from the identically charged spheres. They have the same charge, they're going to pull each other apart. But then they're also fighting against gravity, right? So let's think about this for a second in terms of what forces are acting on here. We do know that there's going to be a repulsive force horizontally outwards. Okay, so let's call this F(U). So that force is going to be pushing everything apart. But there's also going to be, a tension force and a gravity force. There's a tension force on the string, and then it's normal to the force of it pulling down, which is going to be made up of 2 forces. Force of gravity pulling it down, and then this force here, which is going to pull it back. Whoopsies. So we can say that these 2 forces, this diagonal one and this horizontal one, are going to add to give us gravity. Okay, that's how we can connect the force of gravity to that. Okay. So as you can see, as we pull this up farther away, this guy keeps getting larger, and there's more and more wanting to pull downwards. That's how remember we looked at pendulums. Okay, but I'm setting it up this way. Notice typically when we had a pendulum, we set it up this force of gravity and this. But in this case, because I can see that my repulsive force is horizontal, I broke up the components so that I would have a horizontal attractive force from gravity pulling downwards. Okay, so we can just say quite simply that the force Q, right, pushing it to the right, is going to be equal in magnitude to this piece here, which is what's that going to be? That's going to be, this is my angle theta as well. So this is my negative, my tension force. How's that going to work? What's that? That's going to be FG. What do you want to call that? FG horizontal X, let's say. And what's that going to be though, right? We know that. Make our life simpler. Let's just call it FX. Call that FX. Okay. And I know, looking at this, that the tan of the angle is going to be equal to the opposite, so Fx divided by G. Right? So then Fx, right, following along here, Fx is going to be equal to Fg theta. Okay? Write that here. Fg tan theta is equal to Fq. All right? So, rearranging this, that tan theta will be equal to the repulsive force divided by the attractive force, Fg. Oh, that's difficult to read, isn't it? G. So we end up with going to be K charges. Let's just call them Q. They're identical. Call it Q squared divided by the distance between them, R squared. And then we're going to be dividing by Fg, which is going to be masses, the mass of the thing pulling down, divided by G. And when I work all that out, plugging in all my numbers, I get an angle of 22 degrees. Okay, when I plug in all that stuff into there and take the inverse tan, 22 degrees. Okay, so that's a little bit complicated. One very similar to this. For which was this? This is number 7. But in this case, they're both able to swing, and it tells you the angle, and you just have to figure out what's asking for the magnitude of the charges on each sphere. Okay, you're starting for Q instead of theta. All right, so basically pretty long. This is 47 minutes I've been talking so far. So let's go back quickly. What did we learn today? The electric nature of matter. So what do we got here? Grade 9 review, positive and negative. Electrons move. Moving electrons make electricity, and we have law of electric charges. And we learned just now that the law of electric charges is buried in Coulomb's law. Okay, it's hiding, it's multiplying of the charges if they're the same sign same sign or opposite sign. All right, and we did an example of using Coulomb's law. Means balancing charges, 3 charges altogether. Okay, so why don't you go and try these? I will post this video and the solutions to these problems in a minute. All right, take care.